calculator died.
So what we're going to do today, just introduce you to the natural base E, and we're going to simplify natural base expressions. You can graph them because you can use your graphing calculator, right? And then there's a couple word problems that we're going to figure out too. Okay? So we already did that. Okay. So it says the history of mathematics is marked by the discovery of special numbers such as pi and I, the imaginary unit. Stuff we've talked about this year. Another special number is denoted by the letter E. It is called the natural base E. This expression, 1 plus 1 over x to the x power, approaches E as x increases. Okay, and they give us a table of values for that and a graph. Okay, so here's our expression, 1 plus 1 over x to the x power. When I put 10 in for x, we get 2.59374. When I put 100 in for x, we get 2.70481. When we put 1,000 in for x, we get 2.71692. Then they put 10,000, 100,000. Then they put 1,000,000 in. And as this x value gets bigger and bigger and bigger, the number that this expression here, 1 plus 1 over x to the x power, approaches this number, 2.7128. And it goes on forever, just like pi. It's an irrational number. That decimal part never repeats, never stops. Okay, just keeps going on forever. Okay, so this asymptote here, remember an asymptote is a line that the graph approaches but never actually touches. That dashed red line is the E value. Okay, you don't have to memorize what E is. You know, you guys know pi is 3.14, right? But E is in your calculator. Okay, there's two spots you can find it. If you look above your division bar or your division button, you can see the letter E. So if you hit second divide, you can hit E and then hit enter, and it'll give you what that number is out to however many places that is. What is that? 9 decimal places? 10 decimal places? Okay. The other spot you can find it is if you look here along the left side of your calculator, the LN button for natural logs. We're going to start talking about logarithms tomorrow. Okay. Well, this is called the natural log. You can see E to the x power. So if you hit second LN, all right, if we take it to the first power, what's E to the first power equal? Itself, right? You can do that. But you're going to use that one, E to a power, in the word problems. Thanks. Okay? So there's the two places you can use it, but you'll probably use the second LN one more than you will the second division one. Okay, when we get to some problems, usually just for the word problems. So give us some formula to use, and we'll use that E to a power. Okay? All right, so simplifying. If those were x's, x to the third times x to the sixth, what would you do with the exponents? Add them. Well, since they're e's, what do you do with the exponent? Still add. So that's E to the what? 9. Guys are so smart.
Oh, yeah.
Okay. Same rules. Just a variable, right? Same base. You add the exponents. What if you're dividing? What do I do with the 16 and the 4? You get what? 4. What do you do with the exponent since you got an E in the top and the bottom? Right. Where's the E going to stay, top or bottom? Y in the top. bigger exponent. Very good. So what's 5 minus 4? 1. Okay, what if the 5 was in the bottom and the 4 was on top? What would our answer be? What if it was just switching the exponents, making that a 4 and this one a 5? What's the answer? 4 over e. Yes, very good, AJ. Where's the higher exponent? In the bottom. So where's the e stay? In the bottom. Then we just subtract 5 minus 4 again. Okay? See the difference between the two? Same rules. Okay? And we can just leave it in that form. Now, everything inside here has to go to what power? The second. So what's 3 to the second? 9. And what's the rule when I have an exponent inside and one outside? We multiply them. So it's e to the what? Negative 8x. Now, do we like leaving our answer with a negative exponent? No. So what do I do with that? Very good. So the e drops below, and then the negative 8x becomes positive 8x, right? Questions on that? So far, so good? Just simplifying. Same rules you're used to, right? Okay. This one's a little tricky. Okay. What's another way I could write that with exponent? What exponent is square root? Not second. 1/2. Good, Connor. Okay. So when you have a variable in here, it's a little easier if you write your square root as the 1/2 power. What if it was cube root? What's the exponent? 1/3, right? Remember that? What was 4th root? It was going to be 1/4. Remember that stuff? Okay, so that's all we did. Now, what is, you can think of it as square root of 4 or 4 to the 1/2 power. That's a 2, right? Square root of 4 is 2, right? Correct. Now, what's the rule with the 2x and the 1/2? We just had it up here. What was this rule here? How do we get negative 8x? What do we do with those? We multiply. So what do I do with the 2x and the 1/2? And what is 2x times 1/2? 1x. Yeah. So that makes it easier to do that problem. So if that x wasn't there, the square root of 4 is 2. The square root of e squared is what? Oh, what did I forget? I forgot the e. My bad. I'll just see if you guys were paying attention, right? Sorry about that. All right, so if that x wasn't there, it would just be 2e, right? So, again, to help you with that type of problem, sometimes it's to your advantage to change square root to 1/2 power. Okay? And we're just going by rules of exponents. Power to a power, we multiply. Same base, like the first example, we add the exponents. Okay? We have division, we find where the higher exponent is, that's where the variable stays. All right, we good with all those rules? Just kind of a review, right? Still works. Not quite, we're almost done. All right, so 4 natural base functions. Okay, we're looking at this one here. Y equals a e to the rx power. Okay, that's called the natural base exponential function. All right. when A is positive and R is positive, it's an exponential growth, right? When that R is a positive number. So if that exponent's positive, it's exponential growth. If the exponent becomes, what's this R less than 0 mean? Negative. Again, the A value is positive. This number in front is positive, but the R value or the exponent is negative, then it's exponential decay. All right? And then here's what e to the x looks like. And here's what e to the negative x looks like. Again, that's what we're used to seeing for growth and decay graphs, right? And we can just put that in our calculator if we need to. How do I graph something in my calculator? Yeah, how do I do that? Yeah, my y equals button, remember? So you got your y equals button, right? If I want to do e to the x, all right, goes second natural log. Okay? I was going to sneeze. Sorry.
Bless you.
Thanks. So hit second natural log to get that e to the caret. So you're raising it to a power. Then put our x in there. All right? And then we can hit graph. Okay. How do I get it to look like I need it to look? How do I get it to the basic or our standard window? Zoom what? Zoom 6. Thank you. So there's our e to the x. If I want to do e to the negative x, go to my y equals. Again, I'll just go down and do that one as well. Again, second natural log, ln, and then put negative. Remember, negative's down here at the bottom. X. Close it up. And then you get graph, and you'll see the other one come down. Okay? So if you have to graph anything for homework, just put it in your graphing calculator, okay? You don't have to do it by hand. But we can always do it by hand, right?
It's just harder.
What do we like to do if we have to do it by hand? Right, we don't like to do it, but if we have to, we do this, right? We can always do that for any equation, right, Mason? We can do that for any equation if we're trying to graph it. Okay, but again, we have graphing calculators, so we're going to use it. All right, so I'm going to use my graphing calculator. Go ahead and put this one in. Okay.
Here, Caleb. I don't know how to use your calc. It's so funny.
Just for practice, come on, let's do this, please.
I don't have the calculator emulator. You have the real one. I think the emulator is better. How does this work then? Y equals.
Okay, so again, go to your y equals. Anybody having issues with that? You can look at your table of values if you want. Okay. Anybody have a problem with that one?
No.
Okay. Let's do this one. See what that looks like. Is that, first of all, I should have, it says, is it growth or decay? Which one is this? Y.
Bigger than 1.
Well,
0.
what's my exponent?
It's supposed to be negative.
So is my exponent positive or negative? Positive, so it's growth, right?
Negative would be.
So what's this one going to be? Since that's negative, that's going to be decay. We see where we have to look for these?
Yeah.
Okay. So look at the exponent for growth or decay. All right. So I'm going to get rid of that 3. And then I got to make that a negative 0.5 x. Then close it up. I have to close it up. You might not have to. And there's Everybody doing okay on those?
Yeah.
That's pretty easy, right?
Almost.
No, not quite there. Almost.
We're begging for you at this point.
Okay. So, on our last quiz, we had compound interest problems, remember? And this was our formula. P represented what?
The total initial.
Initial amount, right? We call it the principal, right? What you start with. Okay? R was our what? Our interest rate, right? What do we do with the percents? Move the decimal over
2 times.
2 to the left, right? So move that decimal point over 2 to the left. And told us how many times it was compounded in a year. If it was weekly, what was that N number? 52, right? Not how many days in a week, how many weeks in a year, right? This is per year. If it was monthly, how many months in a year? 12. It was daily, 365, right? And then T represented the number of years. Caleb? Yes.
I have it.
Listen, focus. We remember that formula? Okay, well, there's a new one today when it's compounded continuously. Okay? When it's continuous, it's this one. I call it the PERT formula. A equals PE to the RT power. Okay? Where's that E come from? That's that natural exponential function, right? That's that second natural log button. All right? P is still what you start with, the principal. R is still your interest rate. Move the decimal point 2 places to the left. T is still the number of years. Okay? Scribbles? All right? So we understand what we put in. So remember, that E value is from your calculator. Second LN button gets you this look in your calculator. That's what you want. Okay? And then you multiply your 0.05, let's say it's 5% for 10 years times 10. Okay, whatever those are. So let's look at a problem. It says you and your friend each have accounts that earn annual interest compounded continuously. Okay, the balance A in dollars of your account is modeled by this. So what's the principal? $4,500. What's the interest rate? 4%. How many years we're going to use? 10. Okay? Your friend's account is graphed. What's the principal? 4,000, where it started. We don't know the interest rate, right? But we know how many years, right? These years are going by twos. 2, 4, 6, 8, 10, 12. You see that? Okay? And then each line here is going by 1,000. 1,000, 2,000, 3, 4, 5, and so on. You guys understand the graph for your friends? Okay? So, here's the question. Which account has a greater principal? Yours or your friend's? Yours, mine, right? Because it was how much? Right. So mine was 4,500. All right. Who has a greater principal? Okay, we said it. Which is a greater balance? Okay. So let's plug in my 4,500. Go ahead and do that. Oh, I don't need to put parentheses, do I? E to the 0.04 times 10, right? Power. Which is just moving the decimal point over one, right? So you just put 4,500 E to the 0.4 power. What'd you guys get for that? 4,500 e to the 0.04 times 10. Landry, get it?
I got 6,718.
That's what I got.
0.211, so 21 cents. Do you guys agree with that?
Yeah.
Okay. Now, let's look at the graph. At 10 years is here, right? Okay. How much is that? How much money is that? Over 7,000.
Yeah.
Right?
Mm-hmm.
So, after 10 years, did you have more money or did your friend have more money? Your friend. Do we understand how to do that problem? So you started out with more, but after 10 years, your friend. So, you okay, Colin?
Yeah.
So, we could, once we learn how to, once we talk about logarithms tomorrow here, we'll learn how to solve equations, and we could figure out the interest rate there. But it's probably a bigger interest rate, right?
Right.
You start out with less money, but after 10 years you had more money, you're probably getting a better interest rate. Okay?
Yeah.
So you make more per year. All right. Homework. Those make sense? All right. Good job today. Good to see you back.
My window. Homework.